Okay, now under the unit of temperature, you're really just learning about what is temperature in general. When you're talking about temperature, the assumption that you guys may have thought was that temperature is a measure of the degree of hotness of a substance. Some of you, when you thought about temperature, you may have thought of temperature as this is a measure the degree of hotness of a substance, how hot it is or how cold it is. Then subsequently, when you guys think of that, and you might have then come to another conclusion that temperature is therefore a measure of the heat energy in a substance. Okay, so the first thing you might have thought was that, okay, temperature, since temperature is telling you how hot a substance is, in turn, that one will also mean that temperature is a measure of the heat energy in a substance. In other words, in your case here, if temperature increase, the heat energy would increase. Now, this particular statement in itself, the second statement in itself, is not necessarily true. Okay? This statement in itself is actually something that people always mistake. It is not always true. Okay, this is not always true. Temperature is not a measure of the heat energy in a substance. Yes, it will tell you how hot or cold a substance is, but it doesn't tell you the amount of heat energy contained in a substance. Okay, under your temperature, under your ideal gas chapter, you have learned something about temperature and kinetic energy of molecules. You learn that half mc square is equals to 3 over 2 kT. And then this one in itself is actually the mean kinetic energy of a gas molecule. Hence, then you come to the conclusion that mean kinetic energy of gas molecules is actually proportional to temperature. Okay, so yes, temperature you will say is a measure of how hot or cold a substance is, but it's more accurate to say that it is actually telling you the average Ke or particles in a body. That is actually what temperature actually tells you. It tells you what is the average Ke or particles in a body. Okay, now temperature in itself is formally defined as the property of an object that determines which way heat will flow between it and another object. Okay, in general, I think I mentioned this to you before. Heat energy will always flow from higher temperature to lower temperature. Okay, temperature being the property that determines which way heat energy will flow between it and another object. You just need to know that heat energy will always flow from higher temperature to lower temperature. Okay, so case in point here would be something like this. If say for example I have, maybe I don't do this example, maybe I use a separate diagram. Okay, say for example I have a tub of water. Okay, I take a very big tub of water, I fill it with water, this one being my water here, and I tell you that this tub of water has temperature 40 degrees centigrade. Okay, then I tell you I have a metal rod, this one here, I have a metal rod at say maybe 100 metal rod at maybe say 95 degrees centigrade. Okay, so I have a very large tub of water which is at 40 degrees centigrade, and then now I have a metal rod at 95 degrees centigrade. Okay, if you look at the volume difference between the metal rod and the tub of water itself, or rather if you consider all the molecules of the top, all the molecules of the water inside the tub versus all the molecules in the metal rod, you can actually say that this one has higher heat energy contained. This one has lower heat energy contained. Right? It could be that maybe this one contains 10,000 joules of heat energy inside. Okay, maybe this one contains 10,000 joules of heat energy, and then this one being a very small volume containing very small number of molecules probably only contains a much smaller number of heat energy compared to this. Maybe this one only has 500 joules. Okay, so now you see there's a difference in their temperature. There's also a difference in the amount of heat energy contained. If you were to put your metal rod inside right now, inside the water right now, the rod being at 95 degrees centigrade and then your water being at 40 degrees centigrade would mean that heat energy will actually flow from the rod to the top of water. That means something like this will happen. Heat energy will flow out. Heat energy will actually flow out from the metal rod to the top of water. So now in your current case here, you will notice that although your metal rod contains a lower amount of heat energy compared to the top of water, which contains 10,000 joules of heat energy does not flow from higher heat energy to lower heat energy. It doesn't work that way. The thing that will determine which way heat energy will flow is just strictly speaking the temperature. Only the temperature will determine which way heat will flow, not the heat energy. Okay, there's a misconception that people always think heat energy will always flow from the body with higher heat to the body with lower heat. That is not true. It always flows from body with higher temperature to lower temperature. It could be a case where the body with higher temperature has lower amount of heat energy, but the body with lower temperature has higher amount of heat energy. In your case here, it doesn't matter. Heat will still flow from the lower heat energy to the higher heat energy. Okay, so that is what's gonna happen. So when this happens, what you eventually end up with is something like this. You again have your tub of water. Okay, sorry. You again have your tub of water. As your heat energy flows from the rod to the top of water, your heat energy will now cause your temperature to rise, the top of water temperature to rise. So now it could be that this one originally being 40 degrees centigrade, it may suddenly 40 degrees Celsius, it may suddenly rise up to say maybe 55 degrees Celsius. And then the metal rod that you have would have its temperature drop from maybe 95 degrees centigrade to 55 degrees centigrade. Okay, so here if you look at the amount of heat energy that they contain, it could be that maybe this one originally had 10,000 joules of energy. It suddenly added maybe 250 joules, so it becomes 10,250 joules. And then this one originally, the metal rod had 500 joules of energy, but now because it lost 250 joules of energy, this one lost 250 joules, you now only have 250 joules remaining. Okay, so when you put something with different temperatures together, heat energy will always flow from the body with higher temperature to the body with lower temperature. Okay, that's the only thing we look at. Okay, so as your heat energy keeps flowing from the body with higher temperature to the body with lower temperature, the object that gains heat energy will have its temperature increase. The object that loses energy will have its temperature drop. This part here is where heat energy is gained. This part here is where heat energy is lost. So the thing here is that you just need to know that, yeah, the temperature here will keep increasing, the temperature here will keep dropping because of the difference in temperature between them. As long as you have a difference in temperature between them, heat energy will always flow from higher temperature to lower temperature, okay? But the thing is that the heat transfer will not continue indefinitely. It will eventually stop. It will eventually reach something like an equilibrium state, which we call as thermal equilibrium, defined in your notes as this. Thermal equilibrium occurs when both bodies have same temperature and there's no net heat transfer between them. When you put two bodies with different temperatures together, because of the difference in temperature, heat energy will flow from higher temperature to lower temperature. Eventually, both will reach something which we call as thermal equilibrium, where both objects actually now have same temperature and there's no net heat transfer between them. Okay, the keyword is no net heat transfer. All right. So in that case, once you reach this state here, you no longer have any heat transfer, no net heat transfer, your temperature won't change any longer. Okay, so that is what this thing actually means, right? Thermal equilibrium occurs when both bodies have same temperature and there's no net heat transfer between them. So whatever I just mentioned here is actually summarized here. So there's one question that you can do from there. Look at the other sheet of temperature questions that I gave to you 2 days back. I believe that one is page 18. Have a look at page 18. It is not your past year question booklet. It is the separate temperature questions that I asked you guys to print out. Have a look at page 18. This is November 9P41. So the question here mentions something about temperature, right? Let me have a look at it. Yeah, so I'll just close this one off. Clean this. Okay, a student states quite wrongly that temperature measures the amount of thermal energy or heat energy in a body, right? State and explain two observations that show why this statement is incorrect. So as I mentioned to you just now, temperature tells you how hot or cold an object is a measure of the kinetic energy of the molecules, but it is not necessarily a measure of the heat energy contained inside a body. That is a common misconception. So what statements, what observations that you know can explain to you that temperature is actually not measuring the amount of thermal energy in a body? Okay, so one case I could give you is there's actually three different cases. The first one that I explained to you is that temperature only tells you the direction of heat transfer. Regardless of the object in thermal contact, heat will always transfer from high to low temperature. The example that I used just now for you was the example of the metal rod and the tub of water. I told you that the metal rod has lower amount of heat energy, but the tub of water has a larger amount of heat energy. And then in that case, temperature will always just flow from higher to lower temperature, regardless of the amount of heat energy they contain. So that one was that example. All right. There's also another example which I can give you. I could also still give you the same metal rod. Just now I told you it was 95 degrees centigrade, right? This is metal rod, small. What if I give you a very, very big metal rod like this? This is also the same metal rod, but this one is big. And I tell you that this is also at 95 degrees centigrade. Can I say that the amount of heat energy contained in this small metal rod and the amount of heat energy contained in this big metal rod are the same? I cannot say that, right? So that one is this one. You can have two objects of different masses at same temperature. Even though they are the same material, they actually would contain different amount of heat. Since I thought about mass, I might as well give you some mass. Could be that maybe this is 1 kg. This one probably is 100 kg. But they are the same temperature. But it doesn't necessarily mean that this and this have same amount of heat energy. No, it cannot be true. Right? So this is one observation. There's another observation which can also tell you that temperature is not an indication of heat energy. Not necessarily an indication of heat energy. That one is your third example. When you melt or boil a substance, you know that you need to put in heat energy to it, right? But does the temperature change? For this example here, if I tell you I have a block of ice, I melt it to become water. At melting point, this one is 0 degrees. It will become water at 0 degrees also, right? At melting point. Ice will become water at 0 degrees, right? So during this process here, from here to here, you actually need to have heat energy to break the bonds of the molecules so that it suddenly becomes water, right? So during this process here, you have heat energy added, but the heat energy added does not result in the change in temperature. So this one in itself also tells you that heat energy doesn't necessarily cause a change in temperature. The clear example would be when you try to melt something or when you try to boil something. In those cases here, you have heat energy added, but it doesn't cause a change in temperature. So the gist that you just need to know here is that temperature is not necessarily an indication of heat energy. No doubt it sometimes tells you that if temperature increase, there's heat energy being added, but there are cases also where there's heat energy added, but the temperature doesn't change. So it doesn't really give you the indication of heat energy all the time. Okay. So I can also tell you at boiling point is the same case. It's the same diagram now, but I just illustrate to you. At boiling point, if you have water and then it changes to steam, this one will also be at boiling point, water changes to steam at 100 degrees centigrade, right? During this process here, you again have heat energy added. So same thing occurs here. You could have heat energy being added, but it doesn't cause you to have a changes. It doesn't cause you to have a change in temperature. Okay, so that's the reason why you can say this. That's the reason why you cannot say this. Temperature measures the amount of thermal energy in the body. Okay, you cannot say this. This is not necessarily true all the time. Okay, it's not necessarily true all the time. Sometimes you can kind of guess and you can kind of deduce that if temperature change, there must be heat energy added in. But sometimes you can, but that one is not true for all cases. Like for example, like boiling point and melting point. If say for example, I'm not at boiling point, I'm not at melting point, maybe I just have a solid here at 40 degrees centigrade. Then after that, it becomes a solid at say 75 degrees centigrade. In your case here, I see that the temperature change. I can say that there definitely must be heat energy added. So in this case here, yes, the temperature here is actually a measure of the heat energy added. but it does not apply for all cases, especially when you start to look at changes in phase. So that's why I say it is not necessarily true for all cases. Okay, so these are the 3 examples you should know. Right, so if that one is fine, then I will just move on to the next part. Okay, so the next part talks about temperature scale in your chapter. All right. Okay, now when you want to measure temperature, you will tend to make use of a thermometer. The thermometer that you guys are very used to seeing is your liquid in glass thermometer in your chemistry lab. All right. Now, in principle, you know that for your liquid in glass thermometer, your liquid in glass thermometer contains mercury inside. Let me clear off this drawing. Your liquid in glass thermometer that you know looks like this. And then inside it, you have a bulb that contains mercury, Hg. It contains mercury, and then there's a small capillary here for your mercury to rise up or down, right? You rise up, you rise down, and then there's actually some sort of scale here to tell you the temperature, to indicate your temperature. That is the one that you are most used to seeing. So thermometer, yes, is used to measure temperature. But the thing is that when you're talking about using thermometers to measure temperature, you need to know that thermometer makes use of something called thermometric property to measure temperature. Thermometric property is just simply a physical property that varies with temperature. The easiest one is expansion of a liquid in glass thermometer. You know that when you heat liquid up, when you heat up liquid, the volume expands. So what you're doing here in a liquid in glass thermometer is that you heat it up, hoping that the heating will cause the liquid to expand. So when it expands through the capillary tube here, and then it will indicate to you the temperature. Okay, but this is not the only way of using, this is not the only way that is used in a thermometer. There are other ways also that are used in a thermometer. So there are other thermometers that make use of different thermometric properties. The other thermometric properties could be this: change in pressure of a gas at constant volume, which is used in a constant volume gas thermometer. The thing here is that you know that if you have a gas flask here and you fill it with gas, if you heat it up, your gas will have increased in pressure, isn't it? So you still have the same gas flask. The gas flask ensures that the volume of your gas remains constant. When you heat it up, your gas is at higher pressure. So the idea here is that the higher your pressure, the more you heat it up, the higher your pressure will become. Here, your pressure is an indication of the heat energy that you add, which in turn will be an indication of the temperature of the something, or the thing that you're trying to measure. Okay, so here we say here, change in pressure of a gas at constant volume, which is used in a constant volume gas thermometer. So this one, pressure increases with heat. Now, then after that, we talk about change in resistance of a thermistor or other semiconductor, which is used in a resistance thermometer. You also know that if you're talking about certain substances, like say metal or semiconductor, the resistance of conductor or semiconductor changes with heat, isn't it? In your band theory, you learn that if your conductor is supplied with heat, its resistance will increase. But for a semiconductor, when you supply it with heat, its resistance will drop. So you know that the resistance will change with heat. So that one in a way could also give you a measure of temperature. All right. And then the last one here is what you call EMF produced across the junctions of a thermocouple thermometer. Now, this one I won't explain so much about it. Thermocouple is actually consisting of two wires twisted together at the ends. Right? It actually looks like this in page 1 of your notes. It actually looks like this in page 3 of your notes. You will actually have a pair of wires that are twisted together at the ends. And the wires are not made of the same metal. Here that I told you that a thermocouple makes use of two dissimilar metal wires joined together as it ends. This wire here is a separate metal, this wire here is a separate metal. The idea here is that if you twist both ends together and you dip both ends in separate temperatures, you're going to have some sort of EMF being produced. So the difference in the temperature here will cause a difference in the EMF here. So your EMF here will actually give you a measure of the temperature. Hence, we tell you this. EMF produced across the junctions of a thermocouple for a thermocouple thermometer. So these are what we mean by thermometric properties. Properties that actually will change with temperature. Properties which we then use to measure temperature in a thermometer. Okay. Now, for all these thermometric properties here, there's a very important assumption that we make. Okay. The assumption here that we make is that thermometric properties actually vary linearly with temperature. This is just an assumption. Okay, but it's not necessarily true. So it's because we assume that thermometric varies linearly with temperature that we can make use of a particular equation to find temperature from thermometric property. In your SPM, I think you may have been given a case where we told you before, if we give you a thermometer and we tell you that the thermometer has no markings on the thermometer, but that thermometer that we were given, we put it under two different temperatures, 100 degrees centigrade. Then after that, the liquid expanded to one particular length, and then we put it at 0 degrees centigrade, and then the thing expanded to one particular length. So in your case here, if your liquid in glass thermometer does not have any markings, you could actually work out the markings on the thermometer itself by doing a simple experiment where you use the thermometer, you dip it inside two different temperatures, you dip it inside water at melting point, and then you dip it inside, sorry, not melting point, you dip it inside water at boiling point, and you dip it inside ice at melting point. Okay, so then after that, the idea was that this difference in the length at 0 and 100 degrees represents 100 degrees centigrade. So from there, you can actually divide out your scale marking into 100 equal divisions. Then that one you will get your scale marking. Okay. But what if we change the question a little and ask you, if I take that same thermometer, and I put it inside some unknown temperature T, and then I get a certain length here, would I be able to work out what is this temperature here, knowing that the length of the liquid at 0 degrees is some value. Maybe this one is say length 100. This one is say maybe length 0. You could actually work it out by using this equation. Now the assumption here was this. If you want to work this out, you will probably have said that temperature T is probably going to be the length at, okay, this one is length at X. Maybe length at T, sorry. Better use consistent symbols here. This one is temperature T. This is length at temperature T. Okay. If you wanted to work out what is the temperature here, probably you will say something like this: LT minus L0, L100 minus L0 times 100 degrees centigrade will give you the temperature of T itself in degrees centigrade. It will give you the value of T itself at degrees centigrade. Why is it that I can use this? Now the reason why you can use this was because you're assuming this case in the first place. You're assuming that the variation of the length with temperature is a linear relation. It's a straight line. Okay, so maybe I should just label the axis wrongly. This one is temperature T, and then this one is length. Okay, so you know that 0 degrees centigrade is here. You know that 100 degrees centigrade is here. Your unknown temperature T is somewhere here. Okay, so if you wanted to work out what is the temperature here, you could make use of this relation here where we tell you that basically it's basically like this now. If I talk to you about the gradients itself, this gradient and this gradient are exactly the same, isn't it? This one gradient of, yeah, this one gradient 1 and gradient 2 are exactly the same, right? So if say I wanted to find this gradient here, this one will be LT minus, maybe I should just mark it off. This one will be M1, M2 lah. Okay. M1 equals to M2. M1 will be L100 minus L0 over 100 minus 0. M2 would be LT minus L0 T minus 0. So eventually, if you go and work it out, you eventually come to this conclusion: LT minus L0, L100 minus L0 times 100. This will give you the temperature at a particular length. Okay, that's what this thing is trying to explain to you. If you have any kind of thermometer that makes use of a thermometric property, and assuming that the thermometric property is varying uniformly or linearly with temperature, you can use this equation here, where X is that thermometric property, which can be your length, which can be your resistance, which could be your pressure, which could be your EMF. Okay? It is always that thermometric property at that temperature minus the thermometric property at ice point over the thermometric property at steam point minus the thermometric property at ice point. The I here represents ice point, the S here represents steam point. Okay, the symbol, the notation here. All right. Okay, now scales that you construct this way or temperature that you measure this way is actually known as your empirical temperature scale, degrees centigrade. All right. So that part is fine. Then the rest of these are just examples of the thermometers that I mentioned to you: degree in glass thermometer, platinum resistance thermometer, thermistor, thermocouple, and constant volume gas thermometer, etc. There is, if you read the textbooks, they will explain to you in detail how each of these thermometers work, but I will not explain it to you because I've never seen it come up in the past year question. It's just a waste of time to explain it one by one. By the time I finish explaining, your lesson will be over already. So I'll just tell you, you want to know more about this, go and read your textbook. I will just tell you the ones that are important, which is how to you use your thermometric property to find out your temperature. All right. Okay, so then that one being done, I might as well go to some question. Okay, now there is a disadvantage of using your thermometer that makes use of the centigrade temperature scale. Now, just now I told you, temperature that you determine using your centigrade temperature scale, which is a degree centigrade, is determined by using this one, this equation, which in turn makes an assumption that your thermometric property is varying linearly with temperature, meaning to say it follows this straight line here. Okay, but there's a disadvantage in that. If you have a thermometer that is making use of your thermometric property, which gives you temperature in degree centigrade or which gives you temperature in the centigrade temperature scale, you will have a problem later on. Because what will tell you is that in practice, thermometric properties actually do not vary linearly with temperature. Okay, they actually vary differently with temperature. Length could vary differently, resistance could vary differently. You already know that for, say, resistance of thermistor with temperature, it doesn't vary linearly like this, right? The actual case is that it varies like this. This one was the assumed relation, but this is the actual relation. So the thing here is that we only assume that thermometric property is varying linearly with temperature. In fact, it actually doesn't. Okay, it's because of this fact here that thermometric property does not vary linearly with temperature that you will have a problem later on. The problem is that if you have two different thermometers with two different thermometric properties, you use it to measure the same material, it will give you two different readings, two very different readings. What I mean by that is this one. If say for example you have water at say maybe 65 degrees centigrade, and then I tell you you have a liquid in glass thermometer, and then after that I tell you you have another thermometer, say maybe a thermocouple thermometer. Maybe say I give you a thermocouple thermometer. This one being a thermocouple. If I dip this one into here and I dip this one into here, this one, the water, the actual temperature is say maybe 65 degrees. When you put two different thermometers with two different thermometric properties inside the same substance, they won't give you this. They will give you two different temperatures instead. It could be that maybe this one will give you 72 degrees centigrade. Maybe this one will give you 61 degrees centigrade. They won't give you exactly the same value. And they won't sometimes they won't even give you the actual value itself. All right, the reasoning is because your thermometric property does not vary linearly with temperature. So if I wanted to show an example, it could be something like this. If this is your thermometric property and then this is your temperature theta, the assumption was that the thermometric property should vary linearly with temperature. This one is actually the ideal case. This is the ideal one where thermometric where thermometric property varies linearly with temperature. But say for example, for the two examples here, I tell you your liquid and glass thermometer and your thermocouple, they actually do not vary linearly with temperature. Maybe this one is your liquid and glass thermometer. Maybe this one is your liquid and glass. Maybe this one is your thermocouple. Okay, right. So the gist here is this. If your actual temperature was say 65 degrees, maybe this one is the actual 65 degrees. By right, at 65 degrees, your thermometric property should be something like this way. How do I read this diagram already? This one is your thermometric properties at 65 degrees. Yeah, your thermometric property at 65 degrees. By right, yeah, the confusion is with those lines here. Yeah, let me just shift this diagram a little, sorry. If you have it at 65 degrees, okay, if you have it at 65 degrees, for a liquid and glass thermometer, at 65 degrees, it is going to give you this property, which in turn gives you this value. For thermocouple, if you follow the actual thermometric property, it's going to give you this value, which in turn gives you this. Maybe I did it the other way around. This one should be say 60 degrees. This one could be 75 degrees. Okay. By right, your actual temperature is going to be 65. According to your actual thermometric property, if it's following linearly, this one is what you get. But in your actual thermometer, the liquid in glass and the thermocouple, what you're getting instead is actually this one for a thermometric property, which in turn gives you this temperature. And then what you're getting instead for the other thermometer for a thermometric property is this, which in turn gives you this temperature. So this one here you get 60 degrees. Here this one you get 75 degrees. Alright. So the gist is that if you are using two different thermometers, you put it inside the same substance, they will not give you the same temperature. That's the basic idea here. Alright. So that part, just leave it first. Then let's do that other questions. There are some questions here that you can do already. Okay, like this one. Look at page 5 of the other worksheet. It's actually page 5. It's the first page of your worksheet already. This one is page 5. Page 5 should be this one. Okay. Right. They tell you the EMF generated in the thermocouple thermometer may be used for the measurement of temperature. The variation of temperature T with EMF E is shown here. By reference to figure 7.1, state two advantages of using this thermocouple when the EMF is about 1 millivolt. So your case here is that your thermometric property is your EMF. Just now I mentioned to you, thermometer makes use of thermometric property, a physical property that varies with temperature. That physical property here will tell you the temperature. Like for liquid and glass thermometer, you look at the length of your liquid after it has expanded. For thermocouple, you look at the EMF that you produce. So here, this is the graph showing you how the thermometric property varies with temperature. This E here is your thermometric property and how it varies with the different temperature. What is the disadvantage of using this thermocouple when the EMF is about 1 millivolt? If your thermometric property is at 1 millivolts, you have two problems with this graph because it's actually going to give you two different temperature readings. It's going to give you this temperature reading T1. It's going to give you this temperature reading T2. Okay, the first one is two possible temperatures can be seen. And the second thing here is that the variation with temperature is not linear. Ideally, you want the variation of EMF with temperature to be linear. So this one is not. That is the disadvantage of this one. Okay, so that's what's bad about this. So if this one is fine, then I'll move on to the other one. Now, an alternative to thermocouple thermometer is the resistance thermometer. Okay, this is another one. This one makes use of resistance as your thermometric property. Now, state two advantage that thermocouple thermometer has over resistance thermometer. Okay, now to make it your life a lot simpler, in terms of the different thermometers you have, your liquid and glass thermometer, your constant volume gas thermometer, your resistance thermometer, your thermocouple thermometer, just know that thermocouple is usually the best one. Okay, thermocouple is always the best. Just like in your communication chapter recently, I told you between the three different wire communication channels like wire pair, coaxial cable, and fiber optic. Fiber optic is the best. So same thing here. With all your different thermometers that you have here, thermocouple is the best. You have a very wide range, it's very accurate, it has a fast response, it's compact, it can be read directly and fed into a computer. Okay. Now, the part that I need to explain to you is the fast response, because of small heat capacity part. If you look at that case here, now why is a thermocouple thermometer much better than a resistance thermometer? One of the reasoning is because your thermocouple has more thermal capacity, so it can measure more, it can measure small changes in temperature. You have a short response time. What do we mean by that is this. If I give you two thermometers right now, maybe I need to draw this one out. Say if I give you two thermometers right now, this one is your liquid in glass. This one again is your thermocouple. If I tell you that this one has high heat capacity, and then I tell you that this one has small heat capacity. High heat capacity could be, say, maybe to give you some values, maybe this one is 100 joules per kg per Kelvin. 100 joules per kg per Kelvin. This one maybe is 10 joules per kg per Kelvin. Okay, so now the one with the smaller thermal capacity or smaller heat capacity will actually have a shorter response time. Okay, because you look at this one, if you want to have a change in temperature for thermocouple, you only need to have a change in heat energy of 10 joules. But on the other hand, for liquid and glass thermometer, if you want to have a change in temperature of 1 degree, you need to have 100 joules. So in terms of which one is actually more sensitive to temperature changes, this one is actually more sensitive. This one can respond to temperature changes quicker. Okay, it just needs a small amount of heat, then after that the temperature will change. But this one would need a large amount of heat in order to display any changes in temperature. So this one we will say can respond to temperature changes quicker. So this one is short response time. Okay. And then another thing about something with smaller heat capacity is this. It does not affect the temperature of object measured. Okay. An object with smaller heat capacity generally will not affect the temperature of object measured. What do we mean by that? Okay, when you want to measure something, say I have these two thermometers here. If say for example now, I want to measure something. Again, this one is the tub of water or tub of something. Maybe this one is at 90 degrees centigrade. Okay. This one is my liquid in glass thermometer A. This is my thermocouple B. Now, say for example, this one is yeah, maybe I just show this one first. If your thermometer A is put here, this one is your thermometer A put here. And then after that, I should draw another one. You have your thermocouple B put inside here. This is a thermocouple B. This one is also at 90 degrees centigrade. Now, in general, when you want to use a thermometer to measure something, when thermometer is used to measure temperature, thermal equilibrium between the substance. When thermometer is used to measure temperature, thermal equilibrium between the substance and thermometer must be achieved first. Okay. When you want to measure the temperature of a particular substance, you generally need to wait for both of the objects to reach thermal equilibrium. As I mentioned to you, thermal equilibrium is when both objects have same temperature and there's no longer any heat transfer between them. If you try to measure something using a thermometer and they do not reach thermal equilibrium, your temperature will actually keep on changing. That is not what you want. If I told you that this is 90 degrees, this is 90 degrees, when you dip your thermometer A and B inside, you need to wait for it to reach thermal equilibrium first before you even take the reading. Because if you don't wait for it to reach thermal equilibrium, your heat energy will still be flowing, your temperature will still be changing. So that is not really a good way of going about measuring the temperature. You need to wait for it to reach thermal equilibrium first before you measure the temperature. Okay. So when you want to wait for something to reach thermal equilibrium, I mentioned to you that before you reach thermal equilibrium, heat energy will still transfer, right? Now, because heat energy will still occur before you reach thermal equilibrium, your heat capacity of your thermometer itself would actually be a factor in the temperature of the object being measured. You see, if for example, I tell you already that my thermocouple is originated at say maybe I give you a very close temperature. Or say maybe this one, my thermocouple thermometer is 80 degrees centigrade. My thermometer is 80 degrees centigrade. When I want it to reach thermal equilibrium, okay, when I want it to reach thermal equilibrium, I need these two temperatures to be same, okay, right? I need these two to have same temperature. In the process of you reaching thermal equilibrium, if your object has small heat capacity, which one will actually reach thermal equilibrium faster? It should be the one with the smaller heat capacity, right? Correct? The one with the high heat capacity would need a larger, would take a longer time to reach thermal equilibrium because it requires a larger amount of heat. You to get a Kelvin or temperature change, you need 100 joules. But for this one, to get a Kelvin or temperature change, you need 10 joules. So in the process of you trying to reach thermal equilibrium for the two thermometers, this one will actually take a lot more heat energy away from your substance being measured. This one will actually take a little heat away from the substance being measured. What I mean by this is this one, small heat capacity, small heat energy taken from substance. Therefore, original temperature is not affected as much. Therefore, original temperature is not affected. But if I have something with large heat capacity, like this one has large heat capacity, you will have large heat energy taken from substance. Therefore, original temperature is affected. Okay, by right, when you want to measure something, you don't want to describe the amount of heat energy contained in the object. If you describe the amount of heat energy contained in the object, you will change the temperature. So whatever temperature you're measuring is no longer accurate. So you don't want to disrupt it. Okay, but the thing is that when you put your thermometer in, you need it to reach thermal equilibrium first. It will have to draw some amount of heat energy away from your object that you are measuring. If you have small heat capacity, you're not going to take a lot of heat away, so you're not going to affect the original temperature as much. But if you have large heat capacity, you are going to draw a lot of heat away from the substance. You're going to affect the temperature. Okay? So that is one of the reasons why we like something with small heat capacity. It will have short response time. It will not affect the temperature of the object measured. Okay, but that one is not listed here lah. Okay, the ones that we just say was small thermal capacity or small heat capacity, it will lead to shorter response times, that's all. And then another thing here is that thermocouple does not require power supply. Resistance thermometer needs a power supply. That's the second advantage. Okay. And thermocouple is generally smaller than a resistance thermometer, so readings can be taken at a point or is physically small. That is what thermocouple is. All right. I'll look at the other separate worksheet that you guys have. I think you need to look at page 10. Have a look at page 10. It's actually the page after the ones that you just did, maybe. Yeah, it's the second page. Okay, it's the second page. Have a look at that one. Try and do that question. Read through the question and try to do that. You have a mercury in glass thermometer used to measure temperature of oil. Oil has mass of 32 grams. and specific capacity of 1.4 joules per gram per Kelvin. The actual temperature of oil is 54 degrees centigrade. The bulb of the thermometer has mass 12 grams and an average specific capacity of 0.18 joules per gram per Kelvin. Before immersing the bulb in oil, the thermometer reads 19 degrees. The thermometer bulb is placed in the oil and the steady reading of the thermometer is taken. Determine the steady temperature recorded on the thermometer. This one has something to do with the reaching thermal equilibrium that I mentioned. You have oil at 54 degrees centigrade. You want to dip a thermometer inside whose temperature is actually 19 degrees centigrade. Before you even take the reading on the thermometer, as I mentioned, you need to wait for this and this, the thermometer and the oil to reach thermal equilibrium. Only then can you take the temperature, right? So the question is asking you what is the steady temperature recorded on the thermometer, meaning to say this is the temperature at thermal equilibrium. You need to wait for this to reach thermal equilibrium before you can even take the temperature. So this one being higher temperature, this one being lower temperature, would mean that heat energy will flow from here, the oil, to the thermometer. So because your oil loses heat energy, its temperature will drop to some unknown temperature. This one, temperature drop. But the thermometer itself will rise to a certain temperature, same temperature T. This one, the temperature increase. Okay. You would say that the heat energy lost by the oil is equal to the heat energy gained by the thermometer. This will drop to the final temperature. This will rise to the final temperature. This will drop to the final temperature. So you get this. You will still use MC delta T. Q is MC delta T. So just sub in your values accordingly. Change in temperature, it doesn't matter whether it's final minus initial or initial minus final. We're just interested in the difference. Okay, doesn't matter which one is which. Just take the larger value minus the smaller value. This one being the larger compared to this, so it's T minus 19. This one being the smaller of this, so it's 54 minus T. So this one, temperature increase because you gain heat. Temperature drop because you lose heat. Alright. So solve it as you would. No any normal maths question and you get your answer as 52.4 degrees centigrade. Alright. So that one should be fine. You get the answer as that. So the temperature of the thermometer that you will eventually read is 52.4. Okay. So the act of you actually putting in your thermometer will actually change the temperature of the object that you're trying to measure. So just now as I mentioned to you, if this one has a very large heat capacity, it will actually take a lot of heat energy away from your substance and it will change your temperature a lot. So you do not want something with large heat capacity, you want something with small heat capacity. Right, so that part is fine. 52.4 as your final answer. Now then after that they ask you to find out what is the ratio in the change in temperature of the oil versus the initial temperature of the oil. Your initial oil temperature is 54. the change in temperature you get, the 52.4 minus 54 will give you your change in temperature. So your ratio in the change of your temperature is this. Ratio of change in temperature to initial temperature is 0.0296. All right. So now the question then leads on to asking you, suggest with an explanation a type of thermometer that will likely give a smaller value than the ratio calculated in A2. Now you see this one here, the ratio is this one, right? Initial temperature over change in temperature. You obviously cannot change initial temperature. This one cannot be changed because they tell you you want a smaller ratio. But this one in itself cannot be changed. Only this one can change. You want to have a smaller change in temperature, isn't it? So you want to have a smaller change in temperature. What type of thermometer would likely give a smaller value of the ratio calculated? Your change in temperature was actually your T initial minus T final. Alright. Under what circumstances will you get a smaller change in temperature? You will need to use something with smaller heat capacity. So you would just say you can use a resistance thermometer or thermocouple. Alright, this is the old answer. Using resistance thermometer. Yes, resistance thermometer also has more heat capacity, that's correct. But a thermometer with an even smaller heat capacity is your thermocouple. So you could just also change this to thermocouple. So as I mentioned to you before, whatever thermometer they ask, the best one is always thermocouple. All right, no need to think so much. Thermocouple all the way. Right, so you will say this answer, or you could just add thermocouple because it has smaller heat capacity. So as I mentioned to you just now, small heat capacity will not draw as much heat away from your oil, so it won't cause a big temperature change. You want to have small ratio right now means you want to have small change in temperature. You want to have small change in temperature means you need to have small heat capacity, so you do not draw away as much heat. All right, that part is fine. Then after that, you look at part C. Part C is they ask you, the mercury in glass thermometer is used to measure boiling point of a liquid. Suggest why the measured value of boiling point will not be affected by the thermal energy absorbed by the thermometer bulb. Okay, now they tell you right now that liquid in glass thermometer is used to measure boiling point of a liquid. Suggest why the measured value of boiling point will not be affected by the thermal energy absorbed by the thermometer bulb. You see, the thing here is that asking you, they are using it to measure boiling point of a liquid. All right. Why is it that the measured value of boiling point will not be affected by the thermal energy absorbed by the thermometer? Okay, now boiling point temperature is always constant. The heating of the bulb will only affect the rate of boiling. What does that even mean? It is just something like this actually. If you have two different things that you're boiling, say originally this is at 100 degrees centigrade. Yes, that's correct. You're heating it up right now. Okay, you're heating it up right now. If you were to put a thermometer with some value of specific heat capacity inside, something like this, you put it inside. The moment you put your thermometer inside, you could say that the thermometer is absorbing some of the heat away from your water. So it could be that maybe this one, the temperature will drop from 100 degrees to maybe 95 degrees centigrade. But because you're still heating it out, it will eventually reach back 100 degrees centigrade, isn't it? And then after that, it will maintain constant there, right? So if you originally were at 100 degrees centigrade, you put thermometer in, you probably drop to 95 degrees, but then you eventually go back to 100 degrees again because you're heating the thing up. Okay, so just why the measured value of boiling point will not be affected by thermal energy absorbed by the thermometer bulb. You put it in, yes, your thermometer will absorb some of the heat, so in turn it causes the temperature to drop, but then you eventually go back to 100 degrees centigrade. Then after that, you will reach thermal equilibrium with your thermometer. So whatever you have measured there will actually still be 100 degrees. That's what this thing is actually trying to tell you. All right. You use that thermometer to measure boiling point of a liquid. Why is it that the measured value of boiling point will not be affected by the thermal energy absorbed by the thermometer bulb? Boiling point is always going to be constant. All right. Your boiling point will always be constant, so the temperature will always be that same value that you measure. Now the second statement is the part where they tell you the heating of the bulb will only affect rate of boiling. The rate of boiling here, you can think of it as just simply how long it takes to reach boiling point again. How long it takes to reach boiling point again. Alright? Heating of the bulb will only affect the rate of boiling. What do I mean by that is this: if you have temperature thermometer with higher heat capacity, you originally started with 100 degrees centigrade, then you go and put in a thermometer with high heat capacity, maybe you will just cause a very large drop in temperature up to say maybe 80 degrees centigrade. Then after that, as I mentioned to you, it will eventually reach 100 degrees centigrade again. But when you compare this one and this one will take a longer time to reach back 100 degrees as compared to this. That is what we mean by this. The heating of the bulb, because you use something with a large heat capacity, so the heating of a bulb, because of it absorbing heat energy, will only affect the rate of boiling, how long you take to reach boiling point again. Right? So that is what we mean by that. This one, longer time to reach boiling point again. That's all there is to it. Alright? That's why the answer is like that. So this one is fine, then I'll just move on. Okay, so this one is fine, then we'll just move on to the next question. I believe the next question is page 10. Go to page 10 of that same worksheet. No, I think we just did page 10, didn't we? Oh yeah, sorry, it wasn't page 5 that I was doing page 10. Go to page 26. 26. Go to page 26 of your worksheet. You have a resistance thermometer and a thermocouple thermometer, both used at the same time to measure temperature of a water bath. Explain why although both thermometers have been calibrated correctly and are at equilibrium, at thermal equilibrium, they are recording different temperatures for you. So this one I kind of explained to you already just now, where if you had two different thermometers using two different thermometric properties, if you try to use it to measure the same object, they will give you two different temperatures. The reasoning was because they do not vary linearly with temperature, right? So hence the answer here. Your calibrated temperature scale in degrees centigrade assumes linear changes of physical property with temperature. It assumes your thermometric property varies linearly with temperature. Okay. However, neither property actually varies linearly with temperature. You only assume it varies linearly, but the actual case is that it does not vary linearly with temperature. Alright. Okay, so then part B. Part B is the one that I need to explain a bit now for you. Okay, you would have seen before this that when it comes to temperature, temperature can be measured in terms of two different units. You would have seen that temperature can be measured in degrees centigrade. This one I need to explain a little. You have seen that temperature can be measured in degrees centigrade, or temperature can be measured in Kelvin. Okay. Okay, maybe this one I have to redo this. Temperature can be measured in degree centigrade, which is this one, and Kelvin. Now, the one where you're talking about degree centigrade just now, I did mention a little how it's determined, right? It is determined assuming it's determined based on this. Wait, where is it? Yeah, this one is determined based on this page here, page 2. The first thing here that we mentioned was that the assumption is that, okay, for degree centigrade, the first thing we say is that it makes use of thermometric property. And then the second thing we say is that it assumes that thermometric property varies linearly with temperature. Okay, this is the two main things that you need to know. Degree centigrade makes use of thermometric property, and that it assumes that thermometric property varies linearly with temperature, which you already know that that is not true. Then the other thing here you need to know is that the two reference point used is usually your melting point and steam point. This one here, the reference point is melting point at 0 degrees centigrade and steam point at 100 degrees centigrade is used as the reference point. So your temperature in degrees centigrade was X, T minus X ice, X steam minus Xi times 100, right? That was what you can see from here. In degrees centigrade, you make use of thermometric property. You assume that thermometric property varies linearly with temperature. melting point and steam point were used as the reference point. So eventually you got this, right? The one I showed you here. Those were the few things that you needed to do to find temperature in centigrade scale, right? But then there are a few problems with using a degree centigrade scale, right? So the thing here was that just now I told you thermometric property varies linearly with temperature. This is not true, correct? This is the first problem with this. And then after that, we told you that your reference point being used is your melting point and 100 and your steam point 100 degrees centigrade. But then there's another problem with this. These values can change with pressure. If you put your ice or your boiling water and you change the temperature a little, maybe you go up high into the mountain and then you try to melt ice and then you try to boil water, they do not exactly melt at 0 degrees, they do not exactly boil at 100 degrees. Okay, these values can change with pressure. So there's a problem with you using degree centigrade scale. The first one was that they are not actually varying linearly with temperature. The second problem is that your reference point that you use is not exactly fixed. It can change with pressure. So an improvement of this scale is your Kelvin scale. Okay, the improvement of this scale is your Kelvin scale. So what's so special about your Kelvin scale is this. We will just tell you, number one, it makes use of ideal gas properties, which in turn makes it independent of thermometric properties. Maybe I shouldn't write this. Or maybe I should just write this now. It makes use of ideal gas law, which is independent of thermometric properties. Okay. The one thing that makes your Kelvin scale so much better than your degree centigrade scale is that it is independent of thermometric property. So just now you notice that your thermometric properties, the one that says to you that it does not vary very linearly with temperature, is the one that causes you problems in measuring your object. So here, your Kelvin scale here, we will tell you that it is actually independent of thermometric property because it makes use of ideal gas law. Okay, and then after that, the other good thing about your Kelvin scale is that it makes use of two reference points which are known to be fixed regardless of pressure. Your two reference point would be your absolute 0 and triple point of water is used as your reference point. Okay, absolute 0 and triple point of water being used as your reference point. Now, triple point of water is the temperature at which all three phases of water can exist. All three phases of water means ice, water, and steam. That's what triple point of water is. It is actually the temperature at which is actually that temperature where all three states exist at the same time. Okay, so the triple point of water is used as your reference point. Your absolute 0 is your 0 Kelvin. Your triple point is your 273.16 Kelvin. Okay. Now, if you wanted to measure something in temperature scale, there's a certain equation that you will use. The temperature in Kelvin it's just a modification of this. You will just use pressure at that temperature minus the pressure at triple point minus the pressure at triple point minus the pressure at absolute zero. Sorry. Pressure at absolute zero multiply by, let me just show you the equation first. I'm actually here. Oh, sorry. Yeah, which is this one. Sorry, I made a small mistake here. Then it will be 273.16. This one pressure at triple point, pressure at zero. Okay, right, sorry, I made a mistake in the equation. It is actually just pressure at triple point times 273.16. Okay, right. In general, if you wanted to measure temperature using Kelvin scale, you will have to use something like this. It's actually your constant volume gas thermometer, but the constant volume gas thermometer here is making use of an ideal gas. All right. So what you do is that you measure the pressure at a particular temperature, you measure the pressure at triple point, then you multiply by 273.16, that one will give you the temperature in Kelvin. The exact derivation of how it comes about, this one I won't go through that. I will just tell you that given in this kind of situation where they want you to find the temperature in Kelvin using a particular apparatus, using a constant volume gas thermometer, this is the equation to use. All right. I'll further add to you that I have never seen this equation being used before. Okay, so that's the reason why I don't really want to explain so much about this one, because the explanation of this will take 30 minutes. So I'm not going to explain this one. All right. So the main thing you just need to know about what's so good about Kelvin is that it makes use of ideal gas law, is independent of thermometric property, and that its reference point is actually different from your degree centigrade scale. And this one, this two is good, is better than this, simply because maybe I need to write this all. This one, these 2 points are good because these values are fixed regardless of pressure. Unlike this one, pressure will actually change the value of your melting point and steam point, but for Kelvin scale, which makes use of absolute zero and triple point water, these values are fixed regardless of the pressure that you use. So that's what makes this better than this. Okay. Now, when you want to deal with temperature in Kelvin, the only good thing that you really need to know is how to change temperature in degrees centigrade to Kelvin. If I tell you temperature in degrees centigrade to temperature in Kelvin, all you just need to do is temperature in Kelvin is temperature in degrees centigrade plus 273.15 Kelvin. Sorry. Okay, plus 273.15. Then likewise, if you want to change temperature in Kelvin back to temperature in degrees centigrade, it will be temperature in degrees Kelvin. Sorry, you want to change to temperature in degrees centigrade, you take your temperature in Kelvin minus 273.15. If anything, this is the one thing that you need to know. This one, I have never seen it being used before, so I don't really bother so much about that. But if you want to memorize, just memorize it. Okay. But this one, you definitely need to know. Okay, this one, you definitely need to know. And this one also. This one, up to you whether you want to know it or not, but I've never seen the question. All right. So that is what temperature in Kelvin scale actually means. All right. So Let's just do some questions on that. If you look at page 26, I think. Have a look at page 26. All right. Okay, right. Let me just save this one here before I clear this one off. Okay, so you look at page 26 of your separate worksheet. Now, they ask you to state in what way is the absolute scale or temperature differs from other temperature scale. The absolute scale of temperature is actually talking about your Kelvin temperature scale. Sometimes it's also called your thermodynamic temperature scale. Okay. When I talk to you about absolute scale of temperature, it actually means your Kelvin temperature scale. It also means your thermodynamic temperature scale. They mean the same thing. Okay, they're talking about your Kelvin temperature scale or thermodynamic temperature scale. They mean the same thing. Okay, so basically what they're asking you right now is how is the Kelvin scale different from other temperature scales? The only other temperature scale you learn is the degree centigrade scale. So here, just now I tell you it does not depend on the thermometric property of the substance, right? So the answer is this. It does not depend on the property of a substance. And what is meant by absolute zero of temperature? Temperature at which your atoms have zero energy. You learned in SPM before that if you have an atom at absolute zero, 0K, the atoms there actually have zero energy. Then they don't move. They have zero kinetic energy. All right. So they have zero energy from that. Okay. That's what Kelvin temperature scale is. Right. So don't need to explain so much. Just know this temperature Kelvin scale is better than most other temperature scale because it does not depend on the thermometric property of a substance. It does not depend on the property of a substance. You can just change this to thermometric property if you want to. And then what is meant by absolute zero temperature, you know that that is the temperature at which atoms have zero energy. So no issues there. So this one is fine. Then after that, have a look at part C. The temperature of a water bath increases from 50 degrees centigrade to 80 degrees centigrade. Determine in Kelvin and to appropriate number of SF the temperature of 50 degrees centigrade. So here, 50 degrees centigrade, change your temperature to Kelvin. This one, as I mentioned to you, just add 273.15. Okay, the part where they ask you to appropriate number of SF, it actually implies to you follow dp of raw data. You see this one is 2 dp, right? When you change to Kelvin, please make sure it's also at 2 dp. All right, you notice that this one is not strictly speaking written in 3 SF or 2 SF. It's written out to 5 SF, right? The reasoning for that is because of this statement here. Appropriate number of SF means follow dp. So this one here got 2 dp. You need to make sure you also follow 2 dp. You don't round it up. It's 323.15 Kelvin. All right. And then find out the change in temperature of the water bath in Kelvin. Somehow you'll see that the change in temperature of the water bath in Kelvin is somewhat equal to change in temperature of water bath in degrees centigrade. I think I did mention something like this to you guys before. If your temperature in degrees centigrade versus your temperature in Kelvin, if I tell you T2, T1, this one is at 80, this one is at 50. The change in temperature would just be 80 minus 50, giving you 30. If this one change to Kelvin, it will be 80 plus 273.15. This one will be 50 plus 273.15. If I take the difference in temperature, this minus this will minus all this, it will cancel off, so you still get 30. That's the reason why this one is just like that. Okay. Difference in temperature in degrees centigrade is the same as difference in temperature in Kelvin. Right, so that is the one thing that you just need to know. That's the reason why I did not bother to change it, because you will see from here they will cancel each other off. All right, common mistakes to do will be to take the difference in temperature in degrees centigrade and then changing it to Kelvin. This is the most stupid thing to do. Right, so you have that answer, then that one is okay. Then the last page that you guys should look at is probably page 22. Right, just have a look at page 22 if you are okay with that. Okay, right. Okay, just have a look at page 22. I'll just finish this off and after that I'll close off the lesson. Okay, now the resistance of a thermistor at 0 degrees is 3840 ohms. At 100 degrees centigrade, the resistance is 190 ohms. When the thermistor is placed in water at particular constant temperature, its resistance is 2300 ohm. Assuming that the resistance of the thermistor varies linearly with temperature, calculate the temperature of the water. So see the statement, assume resistance of thermistor varies linearly with temperature. Just now I told you temperature in degrees centigrade is x T minus xi over x s minus xi, right? And times 100. That one is under the assumption that your thermometric property varies linearly with temperature. So here they already told you that, you can use that here. So this one here being your thermometric property, you're using resistance as your thermometric property now. So this one you just change to R. That's how you got this. So just minus the values, divide one over the other, multiply by 100, you get the answer as 42 degrees centigrade. Right? This is the only instance I've seen where you need to use the equation. Other years I've never seen. All right, so you get that answer. This is the resistance at the temperature that you're trying to measure. This is the resistance at 0 degrees. This is resistance at 100 degrees. The steam point and ice point, so to speak. Okay, so this part is fine. Then after that, I will just go on to your next one. Okay, the temperature of the water as measured on your thermodynamic scale temperature is 286 Kelvin. By reference to what is meant by thermodynamic scale temperature, comment on your answer in 1. Now, the thing here is this. You read this answer first. Let me just go and write something in. The temperature in degrees centigrade was measured as 42 degrees centigrade. But then when I change to Kelvin, this one will become 315 Kelvin. Okay. Now that they're measuring that same temperature of water, they're measuring that same water, but using a different scale right now at temperature in Kelvin. They're measuring straight using temperature Kelvin scale, and then they found out that it's 286 Kelvin. But then this one, when measured in degree centigrade scale, and then change to Kelvin, gives you this. So the thing here is that this and this somehow are not the same. So they're asking you to comment on your answer in 1. What could explain why is this and this not the same? So here is you just saying that the temperature of water measured by thermistor in Kelvin changed to Kelvin is 315 Kelvin. Then after that, your thermodynamic scale, which is this one, we mentioned to you, does not depend on the property of the substance, right? So here, this one should have been the actual one. If this one should have been the actual one. If thermometric property is omitted. But this one here is thermometric property included. So here thermodynamic scale does not depend on property of substance, therefore the change in resistance of the thermistor with temperature is actually non-linear in the first place. That is the answer here. Yes, it's a bit confusing, but that's the best way I can explain it to you. Basically, what you're trying to do is you're comparing the Kelvin equivalent in degrees centigrade and in Kelvin itself. And you found out that both of them are not the same. But why is it that one is not the same as the other? Is mainly because this one does not take into account thermometric property, but this one takes into account thermometric properties. And because this is not the same as this, you also come to a further conclusion that the change in resistance with thermistor here is actually non-linear. If it was linear, it by right should be the same as this. Okay, that is what that thing actually means. Okay. Thermodynamic scale does not depend on property, therefore the change in resistance of thermistor is non-linear. Yeah, okay. So that part should be okay. Then after that, I just go to the last part of your question. Now you have a polystyrene cup that contains a mass of 95 grams of water at 28 degrees centigrade. A cube of ice of mass 12 grams is put in the water. Initially, the ice is at 0 degrees. The water of specific heat capacity 4.2 times 10 power 3 joules per kg per Kelvin is stirred until all the ice melts. Assuming that the cup has negligible mass and there's no heat exchange with the atmosphere, calculate the final temperature of the water. What is your final temperature of your water given the situation that you have here? This one doesn't really have anything to do with your temperature chapter per se. It's more on your thermal properties. You have polystyrene cup with water at 28 degrees centigrade. You now have a cube of ice that is put in the water. The ice is at 0 degrees centigrade. Alright, now they tell you you stir the water until all the ice melts. Assuming the cup has negligible mass and there is no heat exchange with the atmosphere, no heat gain, no heat loss, calculate the final temperature of the water. So you only just consume this and this. So as I mentioned to you, this one temperature higher, this one temperature lower, heat energy will actually flow from water into ice. Okay, whatever heat is gained by the ice would be the heat lost by the water. Okay, so the thing here is that your ice is solid right now. This one is, yes, it is liquid, no issue here. Your ice will eventually melt to become something else at a certain temperature, but it is at liquid. Okay, your ice, when it melts from solid form, it will change to liquid until it eventually reaches some sort of temperature. So to think about the ice, what actually happens is this. For the ice, it will be 0 degrees centigrade solid. You go to 0 degrees centigrade liquid. Then after that, you'll go to the unknown temperature T liquid. Here to here is your ml, here to here is your mc delta theta. So your heat gain by your ice from melting would be this plus this. your heat loss by water will just be MC delta theta itself. So you just sum in the values that you have and you will get your answer. Mass of ice multiplied by specific latent heat. Mass of ice multiplied by specific heat capacity times change in temperature. Change in temperature is actually the unknown temperature minus 0. That's all. Heat loss by water is just going to be some unknown temperature T, also at liquid, right? So this one here will be 28 minus T. This one is temperature drop. This one is temperature drop because lose heat. This one is temperature rise because you gain heat. So here, because your temperature is dropping, this is larger than this, so take 28 minus T, right? Alright, so get your answer, you get it as 16.2. You do not exactly need to get exactly the same answer. At 2SF, your answer should be roughly the same. Alright, so that one should be it for your temperature chapter. Your temperature chapter in itself doesn't come out that often. Whatever I gave you in your worksheet here is basically the temperature questions that I could find from 2002 to 2014. So temperature doesn't really come out that often, despite the fact that yes, there's a lot of things inside there. If you read your textbook for temperature chapter, the questions that do come out in your actual papers are actually not a lot. From 2002 to 2014, you see there's only like 3 or 4 questions here, right? So it's actually not a lot. If you're talking about from your 2015 to 2018 in your past year question booklet, there's actually only 3 questions there. Page 8, page 11, page 17.